In section 7.3, we'll look at depth cameras. Sensors like the Kinect 1, the ACES Action Pro, and Intel RealSense are all sensors that provide us both with RGB, color information, and depth information. These sensors often use some kind of infrared speckle pattern. When you're using this sensor, if you can wear some infrared glasses, you would see a pattern like the one shown in this image. And then by studying the distortion of the projected pattern on surfaces, the device is able to sense depth. These sensors have a unique set of problems associated with light reflection. If the surface is shiny like a mirror or glass, you're going to get reflections from that and lose some of your data. If some of the surfaces absorb light, black surfaces or insulating surfaces, maybe you won't get the same reflection back. There's also going to be some noise that is going to be different from the RGB and the depth data, and that can be a problem sometimes. And the accuracy sometimes can be coarse, not super accurate. We can simulate a sensor like the Kinect in Gazebo, and so let's study that in this simple Kinect model.sacra file located in the simple camera model package. So as we travel to the bottom of our file, we see that we have a camera simulator plugin right here. It's named Camera Link, and it's a depth type sensor. And the sensor is going to be called OpenNI Camera. The field of view is wider than a regular camera and set here to 1.047 meters, and then this is the resolution. Some kind of clipping information, how close or how far the sensor can reach. And then we have the camera controller, part of the Gazebo tag here. We have the plugin with the file name libgazebo-ros OpenNI Kinect. We set it to have an update rate of 10 Hertz. The camera name will be Kinect, and the frame name will be Kinect Depth Frame. We're going to have image topics and depth topics. So here the image topic name is RGB, image raw, and the depth image, which is a little bit like the disparity image we saw with the stereo cameras, is going to be depth image raw. We're also going to have another topic of points or point clouds. This one is going to be depth points, and it's coming from sensor messages point cloud 2. That's the type. And then we still have the camera info topic for the regular colored image. And we have a camera info topic for the depth image. Then we set a point cloud cutoff of 0.3 and no distortion elements down here. Okay. In this model, the Kinect is going to be oriented downwards from a height of 0.5 meters. And then we're going to use this parameter point cloud cutoff 0.3 as a number to avoid getting the beer can to be too close. We want to have that beer can further away, in this case 0.4 meters. Since the surface is 0.1 meters above ground, the distance between 0.5 and then this parameter of 0.4 is just enough to get the camera. So we can launch it with this command. Simple camera model. And this one is the Kinect simulation. So this is going to get us started with Gazebo, spawning the sensor right here. Great. The launch file also includes a static transform that is going to publish the transformation of the Kinect depth frame with respect to the robot model camera link. So this is going to give us a little bit of a relationship here. We can take a look at the frames. So we just have this static transformation right here. We have the Kinect depth frame, and then we have the camera link, and then the camera link is associated to the world. If we see it in our viz, we also get this representation. So you can see the world right here at the origin, and up here we have both the Kinect frame and the Kinect depth frame and the camera link frame. So here's the Kinect depth frame pointing the z-axis downwards, and the camera link is having the x-axis pointing down by the lens in this way, and the z coming out of the top. So that's another thing that the launch file is doing. And this we do this on purpose because it's easier to interpret the Kinect coordinates this way, by having the depth frame z-axis pointing down. So what we want to do now is the same thing as before. Insert the beer can into Gazebo with the face surface pointing to the camera like this. So let's go ahead and do that. We take our beer, place it there, click on the model, rotate it, change the gravity. Maybe translate this slightly to get a better perspective of that. Okay. So if we want to see the point cloud in our viz, we use the point cloud to display, and now we're going to work on the Kinect depth points topic. So here we have the point cloud to display. Activate that and change that topic to points. Immediately we can see an overlay of depth points with RGB information right here. You can change the style of those squares to be points or flat squares or spheres. Depending on the situation, different formats may help more. You can alter the size, and you'll notice that not all sizes are very useful for your representations. And again, you can have decay times, position transformer. Here we're only allowed to work with XYZ, but these can also change to something like flat color, axis color, intensity bit. With point clouds, we can overlay the RGB system. If you want to see the 2D image just with the RGB, not the 3D overlay of depth with RGB, we can use image view or RQT image view, and using the Kinect RGB image raw topic. So I can say brush run, image view, and then do the topic remapping. Sorry, this is RGB image, I believe. Let me double check. RGB image raw. And so here's the image we get from image raw. You can also more easily do this with RQT image view. That no is hanging there. I probably didn't close it properly. But we can also do brush run RQT image view. This opens a graphical user interface for image viewing, and here we can select whatever topic we want to see. So this is image raw, and that's really the one we can appreciate. Also from RViz, you can add a camera display, and by providing the right topic, we can see that image right here. Now this image is interesting because it's showing the 2D image and also the point cloud. If we deactivate this point cloud here, then we get this clear representation right here on the 2D image view. Alright, so there's all those ways to be able to appreciate the images from the depth camera. Some of the things we can note is, so far in simulation or Kinect emulation, the point cloud view is similar to the stereo camera, right? But one of the better benefits is that we get a wider field of view. And another thing that was useful, if we go back over here and I turn on points cloud 2, is that you also get these points, depth points for the ground plane. That is something we couldn't see with the stereo cameras, and that was because the floor was not textured. But here we can do that. Now in the emulated Kinect, we do get a greater field of view. We can visualize textureless objects, and there's no optical illusions. We don't suffer from reflections of any kind. But in the real Kinect, that's not always the case. Here we can have some points drop out from absorption, optical illusions from reflections, some noise or some miscalibration. So it's not always so straightforward. That's all for section 7.3. Thank you.